Uh, Hello, folks. Back after a long time. So I really took a break actually, so that I can bring things in some new manner. So the first question that I'm dealing with today is it belongs to 2024 October November paper 41 and 43, and the number is 9. Is about the chapter nuclear physics and radioactivity, and it has got some tint of PET scanning as well from the medical physics. So it says fluorine 18 decays by beta plus emission with a half-life of half-life of 110 minutes. So 110 minutes. So this 110 minutes. State the name of the beta plus particle. So we know that it is a positron. So we know that it is a positron. So it's positron. Now, second question says, show that the decay constant of fluorine is 18 is this. So for that, we should have first this T half should be noted properly. So T 0.5 should be equal to 110 minutes. 110 minutes, and that's equal to 110 into 60 seconds. Then we have this lambda is equal to 0.693 divided T 0.5, and that will be equal to 0.693 divided 110 into 60. So if I use calculator here, so if I calculate here, 0.693 divided bracket 110 into 60 bracket is equal to, so it comes out to be equal to 1.05, and there is 0.22 as well. I neglect that, into 10 to the power minus 4 per second. So this answer matches with this okay. Now determine the activity of 2.1 into 10 to the power minus 12 kg of fluorine 18. Activity, so activity means dN by dt, or we can say it as simply A as well. So to have activity, we must have the number of particles first, number of those molecules of fluorine. So for that, what we have to know is 1 gram mole of a substance will have Avogadro number of particles. So that means 1 gram of this fluorine 18 will be equal to 18 grams. So that's why 18 grams or 0.018 kg of fluorine will have 6.02 into 10 to the power 23 molecules. So this is 1 gram mole, molecular mass, or we often say atomic mass, molecular mass, and this is Avogadro number. So that's why, therefore, the mass given here is this much. So 2.1 into 10 to the power minus 12 kg of fluorine should have 6.02 into 10 to the power 23 divided 0.018 into 2.1 into 10 to the power minus 12. So when I do calculation, it will give me 6.02 exponent 23 into 2.1 exponent minus 12 divided 0.018 equal to. So this comes out to be equal to 7.02 into 10 to the power 13 kg. Now our activity should be equal to dN by dt is equal to lambda n, and that's equal to lambda is 1.05 into 10 to the power minus 4 into 7.02 into 10 to the power 13, that gives us 7.37 into 10 to the power 9 per second. Okay. Now, so and this can be noted as a becquerel. So becquerel is here. Now, next is a small sample of fluorine 18 injected into the body acts as a tracer for use in medical imaging. Describe how the interaction of a beta plus particle with an electron in the body enables the formation of an image. So What happens is when beta plus particle acts with the electron, we have got E plus E minus will release gamma plus gamma. So it will be two photons. And these two photons will be traveling in opposite directions. They definitely will travel in opposite directions in compliance with the principle of conservation of momentum. Then, after that, they arrive at the detectors around the body. And depending on the difference in the time, the position of that place is known. That place is where they originated, or the tissue, or where this interaction happened. So that will help in determining the position of the thing, and if there are lots of sort of interaction, some irregularities can be observed, and so on. So this is how they uh, and those energies are fed to computers to form images. So that is how it works. Now, next is suggest why. Suggest why 110 minutes is a suitable half-life. So 110 minutes means 2 hours around. 110 minutes mean around 2 hours. So 2 hours is a appropriate time for medical testing. Now, if we have got less half-life, if we have got a less half-life, then this reaction will finish quickly. Will finish quickly even before the test is finished. And if we have a more half-life, if we have more half-life, the radiations would be remaining in the patient even after he or she gets discharged from the hospital. So that is dangerous to himself, herself, or other people around him or her. So that's why we should have a long half-life as well. So that's why this 110 minutes is a very, very suitable half-life.